Good morning, everyone, and welcome to this another day for the Smart Seminar series. It's my pleasure to welcome Yizheng Wang. He's a second-year PhD student in the Department of Engineering Mechanics at Tsinghua University and is also a recipient of Tsinghua Future Scholar Award. He's currently visiting Bauhaus University, Weimar, where he's working with Professor Timon Rabchuk, and he has obtained his master's degree from the Department of Engineering from the very same university, and has followed by a researcher working at the AI for Science group at Microsoft Research. His research focuses on the integration of artificial intelligence and physics-based computation. With that brief introduction, please join me in welcoming Yizheng Wang for his new work on Pretrained Finite Element Method. So, with that, Zizheng, it's all yours.
Okay, thank you everyone. Thank you from Dada invitation. So today my topic is about the pre-trained FEM, which means we use the pre-trained and one-star framework for PDE via Physics-Informed neural operator. Well, there are 6 parts of my presentation. The first part is about background. As you can know, AI now changed the world. So AI for science, it's very popular in the currently, and there are a lot of way by AI for science. For example, AI for material, AI for biology, AI for chemistry, and especially our topic is about AI for PDE. So because science is very big, so today our only focus on AI for PDE. There are 3 important mainstream methods in AI for PDE. The first one is well-known pins. It is very well known. And the second way is operator learning, and the last one is the physics-informed neural operator. So let me literature review about these 3 main methods. The first one is about pins. The pins code, the first one is that we use neural network as an approximation function. For example, traditionally we use the FEM. The FEM, the approximation function, is shift function. However, in pins, we use the neural network to replace with that. And the second one is that the loss functions are constructed using the physical law. So that's why it's called physics-informed. Okay, there are 2 important forms in physics-informed neural operator. The first one is strong form, which proposed about, I think, 7 years ago. It proposed by Kaniadakis group. Is the original pin. It's called strong form. And the second one important form is the energy form. It's proposed by Timon Rabchuk. It's called the deep energy method. So why there are so many people to learn, to research pins? Because there is a theory to guarantee the neural networks can approximate any continuous function, which means it is very good to ask the neural networks as the shift function, like the shift function as the approximation function to solve the partial differential equation. However, pins lack the generalization capability. It is a parallel to FEM. It's only the PDE solving method. And what FEM can do, pins can also do it, because we only change the change approximation function to change from shift function to neural operator, neural networks. So pins can solve what FEM solve, but in a different manner, which can solved by the neural networks. So there are another important domain is called neural operator, which means it can learn the PDE family. So as the last slide, pins can only solve one specific problem. However, in operator learning, it can solve a lot of problems. It's called a PDE family. For example, you can boundary condition and material and the geometry. They are all the input function. But you only want to get like, for example, like the displacement. So it is a mapping. It's an operator. It's called an operator. So if you can change the operator learning successful, it will be very good, because the inference time is very small. For example, in traditional method, you will only cost maybe 1 hour. In operator learning, it will only cost 1 second. Its error is also very small. It's about 1%, empirically. However, in this domain, we use the data to train a neural operator. There are 2 important way in your operator. The first one is DeepNet. The second one is FNO. It's proposed by Li Zhongyi from Caltech and Lulu from the maybe when he's in the Brown University. Okay. So neural operator, it can solve a lot of complex problems. For example, the numerical weather prediction problem. A famous framework is called ForecastNet. They try to use the FNO to solve the numerical weather prediction problem. However, in some months later, I think there is a very clever guy called Bi Kaifeng. He published a paper in Nature. It's called Pangu model. This model can only change FNO to the Swain transformer. So it is a transformer based. It's called Pangu model. So as you can see now, because Pangu is used transformer based way, like the operator learning. So we can see the transformer-based operator, now it will pay more attention. It will show a very good potential, especially in the complex geometry problem. So what type of the transformer-based way in operator learning? There are two important ways in transformer-based way in operator learning. The first one is G-Node. His name is Hao Zhongkai. He's also my first author of this paper, PFEM. About 3 years ago, he proposed a framework based on transformer to solve the problem. However, his complexity of his algorithm is about n squared. About 1 year later, another very clever genius is called Wu Haixu. He proposed a Transolver framework. This is, I think, currently very popular now. And he changed, the most advantage of the Transolver compared to G-Node, it will decrease a lot about complexity. It will decrease from n squared to n. So when you solve the large scale problem, it is a very good advantage. Okay. There is a very important to know that because the transformer, you can only use a point. You only use a point as input instead of the grid like in FNO. Because when you solve a very complex problem, you have to make a big grid. Yeah, it's a big grid in FNO. It's very inconvenient. It's right. Okay. So it is this review about the operator learning. Now I introduce a review about the Physics-Informed neural operator. Physics-Informed neural operator, which means it will use PDE only. Use PDE to train operator learning. And the last slide, operator learning, it will use data. However, currently, a lot of work, they will use only, maybe even only use a PDE to train the operator learning. For example, there are two representative ways. The first one is the Pinot. The second one is Vino. Pinot is proposed about 4 years ago. The first work, I think, is proposed by Wang Siban. However, in his framework, he used DeepNet as a backbone. And some years later, the first author of the Li Zhongyi proposed a Pinot way. It used FNO as the framework. And recently, about last year, my friend Mohammed, he proposed a famous word called Vino. He used the energy form as the loss function instead of the strong form. He published it last year in SMaRT. Okay, you can see. When you successfully train the operator when using the PDE, the error is about empirical. Empirical is about 1 to 5%. However, if you want to get a more accuracy, I think it is very difficult to get that. You must use another way. And okay, now currently we found almost all Pinot framework, they are all built on DeepNet or FNO. They are lacking the transformer base, especially Transolver, because there is a big advantage of the Transolver. The complexity is very, very, very small compared to the traditional transformer base. So, and another advantage, it can operate only on the point instead of grid. Well, the point, the point cloud, is a very big advantage because you can only use a point. It's very easy, right? It's very flexible. Okay, and I want to show you another interesting thing is that recently we try to use the Pinot. It can use its output as the initial solution for iterative method. Because the initial solution is better than the random. Because in traditional we don't know the initial solution. So in Pinot, we can get a good initial solution. So we can use an iterative way to ask the initial solution to iterative that. So we can find about 2 years ago, I tried to this framework in the 3D problem use FNO as initial solution. As you can see, the iterative number will decrease a lot compared to traditional method. And my friend Mohammed, he also proposed the same way, and he verified my idea. It's called NOS, N-O-W-S. Well, this is his iterative number, as you can see. For example, this red line is used initial solution in Pinot. This red line, I mean, is used like the 0 in traditional method. If we want to get the same convergence value, you can see the little number will maybe the 16 having traditional, maybe over 300. Well, you can see this initial solution, I mean, its one start stage will be more and more popular. However, we found all this work are only use like the FNO or deep neural net. There was no one guy to use this framework that's based on Transolver. So we will ask two important questions. The first one is that now almost everyone use FNO or deep neural net. It is a regular match, especially in FNO. Regular match, I mean, it's very inconvenient for some very complex geometry problem. So the first question is, could we use a Transolver as the backbone for Pinot? Okay, because it will bring us a very good advantage. We can only use point without needed a regular mesh. The second problem is the second question I want to ask is that, could we use the iterative way like the one star to make the accuracy better? We can use the Transolver as initial solution and then fine-tune it iteratively. So it will combine, the efficiency of the neural networks and the accuracy of the traditional algorithm. However, there is no one to use this idea, and there is no one to explore this idea, so it's a lack of corresponding research. So let's try it. Therefore, we propose a Pretrained Finite Element Method. There is a very famous painting I want to show you. It's called Wonder Above the Sea of Frog. It's very like our research. We are like our research is like this wonder. When we get the top of the mountain, we want to know which mountain is the highest. We must go down it to practice. Okay, so let me introduce our method. Our method uses a Transolver as the backbone. For example, let me introduce a Transolver. For example, it's 5-point star. We can get each point will get the coordinate and about its material and its boundary or condition. There are all is about the prompt. Okay, we can get like for example, there are n points, so we can get the n point prompt. This matrix, for example, is 4 by n. And then we can use MLP. It transforms from 4 dimension to C dimension. We can get this matrix is C by n. And then we can use the layer norm to make this algorithm more robust and use the physical attention. This is the core idea of the Transolver. The physical attention is that we can get this input like the C by n, and then we can use 2 MLP. The first one is from transform from C by C. So we can get this U matrix. And the second one is that we can transform the C by S. S means a slice number of in the Transolver. So we can get 2 matrices. The first matrix is C by n. The second matrix is S by n. Then we process this matrix slice width, and we sum along the point number. We can get a size norm. This is a vector. The vector dimension is S. Then we process about the first matrix C by n. We use this U and this slice width to multiply them together. For example, we use this because there are C by n matrix. We can use this slice width with one vector. One vector is about 1 by n. So 1 by n multiply this U, we can get one matrix is then shaped with the U is C by n. Because we have S dimension, so we can get there are S matrix. Each matrix are the same shape. It's like the C by n. Then we sum along the n point. So we can get there are s c vector, just c vector. Each vector, I mean the dimension is s. We can get this one, and then we use the slice norm to divide it. For example, this matrix, we can divide it by this value. There are s value, so this value to that, a second value to second one, and the last one is to the last s. As a result, we can get a physical aware token. Please noting that this is s, the sequence is s. However, originally there were n. So s will less more than n. So then we use the transformer to operate on this physical aware token, like the QKV matrix is right. Then we can get output. Its output matrix is about S by C. Then we get this matrix and we use a slice width to dislice it. How to dislice it? For example, this matrix is S by N and this matrix is S by C. So we can multiply this matrix M multiply ZT. So we can get the matrix shape is C by N. Please note that C by N, the matrix is same shape with the input. So we can get the input and output shape are the same. So we can repeat this Transolver layer again and again. It's very like the FNO layer. Okay, there are two key parameters in the Transolver. The first key is that slice number. The second one is the layer number. Okay, then we can use the Transolver as a backbone to replace with FNO. For example, this is a cat. We can get each point of this cat like this gray point that get coordinate, geometry, material boundary. We can get all the points. Then we can use Transolver to get the output. Because the output is wrong. It's wrong, right? Because we don't use any constraint to make this output correctly. So we can use there. However, we have the PDE. So because we have this output and we have the grid, so we can use a shape function PFEM. For example, in our work, we call it explicit function differentiation way. Use this way. So we can get the derivative of the PDE. So we can use like a strong form or energy form, which one you like. You can you can choose any one, and then you can get the PDE loss. If you have data, you will have the data loss. But in our framework, we only focus on purely PDE, no data. So we get the loss. And we minimize the loss, and we can train that parameter in the Transolver. So after this training, it's called the pre-trained stage. It's our PFEM. The first stage is called the pre-trained stage. You can get a low fidelity solution. Okay. For low fidelity solution, if you think the accuracy is good, oh, okay, everything is done. Everything is done. But if you want to make the accuracy better, you can use an iterative way, because we can use a Transolver to get anywhere. I mean, you can get anywhere value. So you can use a traditional method like FEM. Because a low fidelity solution, you can use it as an initial solution. Then you can use a iterative method like the FEM, FDM, FVM. You can choose anyone. Then you can fine-tune. So you will get a rethinking solution. It will high fidelity solution. So I call this stage is called a one-star stage. Okay, as you can see, we use the neural operator, and we also use the traditional FEM. We use the neural operator efficiency, and we also use the accuracy of traditional method. I mean, in the future, maybe if you have a supercomputer, you can use cloud computing. Everyone can use his data or PDE to train, operator learning. This operator learning will give output to each user. For example, research scientist, structural engineering, hydrologist, they will get initial solution from their cloud computing, and they can use their own computer to fine-tune the initial solution. It's called one star, because fine-tune is lower computational time. Everyone can fine-tune it. However, in neural operator, you should have a very good computer. So it is practical to have this one in the supercomputer. Okay, so let me show you some result of our method. The first one is a linear problem, and second one problem is about nonlinear problem. The first one is a linear problem. So the first one I want to show you about the only change geometry, which means the material and the boundary are same. So let me verify, test this framework, whether the framework can work in the variable geometry. For example, in this correction, this is the very famous benchmark. We change the whole. It's from the GRF, it's from the Gaussian random field. The shape are different. However, in FNO, like the Vino framework, we have to get the grid. Like your grid, each one is grid at one point. If in the whole, the value usually be 0. However, in Transolver, we only use a point. In the point, we don't need input. We don't need use the point in the whole. Okay, so we will test PFEM generalization capability in this question, especially for compact geometry problem. As you can see, this is our result. The first line is a reference from FEM. The second line is our framework. It's only the pre-training stage. Is our prediction, and the third line is about error. As you can see, our error is very small. For example, the prediction and the reference are very close. The maximum value is about 0.1. However, the error is the maximum value is only 0.004. So it will our PFEM can prediction about the change geometry very well. Okay, because the transformer-based framework, we only use a point. So we will ask a correction, which make the point less, and it will robust. So it's a correction. So we change the point. In our original training, we use is nearly 37,000 points. So we can use could we use more points to train the framework? Okay, we make it less. It's over 10%. As you can see, the prediction are almost the same with the reference, so it will have a very good robust. Even if we only use 1%, only 1%, you can use this relative error. The relative is only I think maybe 11% error. Only 1% is maybe 370 points. Yeah, it's very. There are very few points in this correction. As you can see, it's very robust. And I will also show some training detail because we can use the X is the epoch and Y is relative error, and this light blue is about STD is about virus. As you can see, it's very robust. So in this empirical result, I will show you that PFEM will have a very good robust when we are training the point number. Okay. For example, we also compare with the Vino because Vino uses FNO. So we will ask a question: how is the result if we compare with the Vino? So the second line is the Vino result. The third line is our result. You can see. Our results are very, very close to the Vino result. However, in Vino, we must use a grid. So it is not very convenient to use this way for a complex geometry problem. Okay, and we also test the fine-tuning stage, which is one-star stage. We use the initial solution from Transolver, and then we fine-tune it. As you can see, the second line is our pre-train stage error. If we use one-star stage and use a iterative way, the error will be 0. Okay, in this B picture, as is very more clear, the original line is about the FEM. Our method PFEM is blue line, as you can see. When we achieve the same error like this black line, we will only use the small iterative number. This box plot will give you the result about the statistic. As you can see, traditional method like FEM, you are over the 500 iterative number. However, in PFEM, we only use about 60 or 70 iterative number. So PFEM can significantly reduce the number of iterations required for convergence. So I will show you the table because the table is more quantitative. It's more quantification. As you can see, this one is energy plate G means geometry. The time in PFEM is 0.02 seconds. Having a traditional method, we are called about 5 seconds to get the result. Relative is very small. It's maybe 1%. It's very, very small. And we can get a speed up is about 6.24 compared to traditional method. Okay, we also compare, because there are two key important parameters in Transolver. For example, layer number and the token. Token means is token is S. The number S can be chosen by the user. So S is different and the layer number are also different. Okay, so we tested a different layer and different S. This S means a token. We can get this result when we get the biggest model. The model is the performance are the best. So it will show you it's like the scaling law in Transolver. Okay, so we increase the difficulty of this problem. We will generate not only geometry but also material. We also the material is also from the Gaussian random view, like this picture. As you can see, the modular distribution, Poisson distribution, and this reference, and this our prediction. Our prediction is very close to the reference solution. The error is very small. We only use 2,000 training sample and 500 testing sample. So this numerical example verify that PFEM can perform well on the complex geometry and the material problem. And this picture is also show some one-star stage. It can also show the same conclusion. It will decrease a lot about iterative number. Okay, in this table is also quantification. You can see the relative error is about 2%, and the time is very, very less compared to traditional method. So, the more exciting conclusion is that we can use you can determine by the user. If the user I think okay, 5% is okay. So it's everything is done. You can only use 0.06 seconds to get the result. It's very fast compared to traditional method. If you use okay, I don't think the result is good. I want to get a better result. You use one-star stage. One-star stage, you can use Transolver as the initial solution. So the speed up will be better than you one-star by the random view, is right? Okay. So let me do the most crazy thing. We generalize everything. That's the geometry, material, and boundary. Everything we generalize because it's the key for simulation. When we change the boundary, change the modular, change the Poisson rates, change the geometry, you must reuse the traditional method again. So we will ask a question: could Transolver can generalize everything? So we try it. As you can see, everything is from the Gaussian random view. Our prediction is very close to the traditional method, and the error is very, very small. So we verify the idea. PFEM can perform well on complex geometry, material, and boundary condition. And we'll also test about the one stage about the iterative number required in this problem. As you can see in here, our PFEM, the iterative number is, for example, this black line, and we plot this in boxing plots. As you can see, is our iterative number. It's very, very small, right? So I think this table is show more clear quantification. As you can see, traditional method will use 900 iteration. However, in our method, we only use 99. So the speed up is amazing, about 9.18, and our error is also very small. It's only 2%. Okay, so in this linear problem, we verify one thing, that PFEM can effectively generalize geometry, material, and boundary condition together. Everything can generalize together. In the other other one paper, they only fix the other and only verify geometry. So in our work, we verify everything. Okay, so we verify this problem in linear elasticity problem. There is also another big advantage is that we use the point cloud input only. only point. So it is very flexible and very convenient. Moreover, we use the Wang start stage and we show a conclusion that PFEM substantially reduce the number of iterations. As you can see, the speed up are very amazing and very interesting. Okay, so this is a linear problem. The second problem I want to show you the nonlinear problem. So we choose a nonlinear problem. There are two nonlinear problems. The first one is the beam problem. The second one is a very famous Cook membrane problem. So why we use the beam problem? Because we can verify this idea. I mean, compared to FNO, because FNO is very, FNO is very suitable to solve this regular geometry problem. We fix this geometry and we change the boundary condition and modulus and Poisson rays in this question. And in our B second example, use a Cook membrane. We will change the geometry, boundary condition, and material altogether. For example, how we change the geometry? We can change the length of that. The left boundary, we can change this length. It will random from Gaussian random view. And in right boundary, you can also change the length of the right boundary. This L is also random, and this H is also random. So the geometry are random. It's from Gaussian random field. We use about 800 training sample and 200 testing sample. Okay, so let me show you the first numerical result of the nonlinear problem. As you can see, this is our result. Our prediction we also compare to the Vino way. As you can see, this first line is boundary matrix, and the second one is the modulus matrix. Third one is the Poisson distribution. Reference solution is from FEM, and our Transolver is the fourth line, and FNO prediction is the sixth line. As you can see, we are very close to FNO, and our error in some case will less than will be less than the FNO. As you can see in here, is right. The prediction about Transolver is better than FNO. We also show the error curve, for example, in B and C. The differences at B and C is that B is the mean relative error, and C we want to test is like the variance. What we want to test is robust of our method. But as you can see, in this way, you can see Transolver can get the same accuracy like the FNO. However, FNO converge faster. As you can see, Transolver converge faster than Transolver. But in the final stage, the final epoch, it will get maybe more good, robust than the FNO. Okay. We also compare to the iterative way. We use initial solution from Transolver. As you can, this is a original line. We use because it's nonlinear problem. We have to use a nonlinear problem like a Newton iterative way, Newton Laplace way, like the iterative way. You can see we also need maybe 2 or 3. Iterative number is enough to get a result. Which will approach the same accuracy like the traditional method in FEM. Having FEM like this blue line, it will make more iterative number. So our PFEM can significantly reduce the number of iterations required for convergence. Okay, so this is a table for the quantification. As you can see, the error is about 6%. And the time is very interesting. Our method, PFEM, the pre-training stage is only cost 0.09 seconds. However, in the traditional method, it will cost about 36 seconds. So, and if we use the Wang start stage, the speed up is very interesting. It's near 4 speed up. Okay, so our PFEM perform, I think, very well on complex material and boundary condition, especially for good accuracy and efficiency. So let me show you the last one nonlinear problem. It's a Cook membrane problem. So we random everything like boundary, modulus, and geometry. It's a boundary for, as you can see, it's random. It's a random Gaussian field, and the modulus is also a random Gaussian field, and the portal is also random Gaussian field. This is for the first line is reference solution, and our prediction is very close to the reference solution, and the error is also very small. So I think these simulations are all we needed in a lot of problems, such as boundary condition, material, and geometry. In our framework, PFEM can generalize them all together very well. So PFEM perform very well on the complex geometry, material, and boundary condition. And we also use the Python, use the one-star stage to test the iterative number. As you can see, we can get a less more iterative number compared to the FEM. Okay, so this table will show you the interesting quantification about hyperelasticity code problem. Okay, the error is about 3%, and the time is very less compared to traditional method. It's only cost 0.1 per second. However, if you solve this problem at the end, because we are cost you 93 seconds. So if you think, okay, 3% error is good, it's good. So you don't need use the one-star stage. Okay, RPM can effectively, I think, generalize across geometry, material, boundary condition on nonlinear problem. Nonlinear problem, we can only use a point cloud input. There is no need to use grid as the input. And we use one-star stage. It will significantly reduce the iteration number required for the convergence speed. That's right. So as you can see, the speed is very amazing. Okay. So let me show you some discussion. There was a lot of discussion I want to show you, but I will choose two I want to show you the most. The first one is we test our model on the output on the out of distribution. What's this meaning? It means we train this data on like the GRF, but we test in another probability distribution Gaussian random field. As you can see, the model can get a very good out of distribution. And the second interesting I want to show you, I think PDE are the complete data source. There are a lot of guys, they want to use the data to train the operator learning. I think it is not a good way because these data are also from numerical solver. That's right. If the PDE are very, very clear, I think in the future, PDE are everything. A PDE can train a neural operator. There is no need to use the traditional numerical, whether to train a lot of data, then to train the data and use this data to train operator. It's very time consuming. I think there is no need. If the PDE is very clear, you use PDE, only use PDE, purely PDE to train the operator learning. Okay, so let me introduce something interesting conclusion. I think there was something you can take home. The first one is that we want to we propose a pretrained finite element method. This method is a purely physical-driven framework. It combines the efficiency of neural operator and the accuracy of the traditional FEM. So I think PFEM in the future will be a new FEM. For example, about 17 years ago, computer brain the emergence of the FEM. Now AI changed the world. So AI will also change. The computational mechanics. It's like AI will bring the PFEM. Okay, I will show you a very famous painting I very like. It's from it's called Forecast Side. It's from, maybe it's France. It's that the scientist, the artist sees the egg. However, he paints the birth. Okay, it's very like our research. Okay, thank you for your attention. Okay.
Thank you, Yizheng.
Okay.
Yeah.
Yeah.
Maybe I would want to ask one question before I open it to the audience. You mentioned about using the iterative solvers. So for the linear problem, which iterative solvers did you check or did you evaluate?
I use the DG iterative solver. Yeah. In traditionally, if the problem is large scale, we maybe use a PCG. This preconditional. DG method. Yeah. DG is very popular in iterative method. However, if we solve the problem, it's very large scale. We are use a PCG. I will write it in the chart like a PCG. Yeah. However, in our method, we use a CG. because in PCG, for example, the PCG, we solve the linear problem, we must to approximate the inverse matrix. So it is no fair to use the PCG. So in our method, we use a CG to compare, to ask the iterative method to literally that. There is an interesting thing I want to show you is that, for example, because you can see, if we use a good, I mean, this line, this solid line, then blue and is red and blue. The red line means we get the solution is not very good. It's from maybe the 0. However, the blue line is from the neural operator. The initial solution are very good. You can see the chain, the chain are same, the slope are same. Because we choose the same iterative method, the convergence rate are the same. So if we get a good initial solution, it will start with a lower point. So if you want to get, if you want to get the relative error, like for example in here, like 10 minus 4, the literate number will be that 30 or 30, maybe 30 number. In if you get a zero solution, zero initial solution, you are getting maybe the 19 or 80. 80 may better, 80 literate number. However, if you make the relative error small and small, very small, there is no need to use the initial solution, because as you can see, this line chain are same. So it may be, for example, the minus the 10 minus 15, for example, 10 minus 15. If you use a good initial solution, you will get maybe the iterative number maybe 900. And if you use the zero solution, initial solution, we will be 930. Yeah, it's only a 30 iterative number you can reduce. So I think if you get, the relative error is more. For example, it's minus 10 minus 4. It's error. Relative error is maybe close to 10 minus 3, 0.001. I think it is enough for most cases.
Yeah. I see. Yeah, I think that kind of answers the person who actually dropped a comment on chat that he was wondering if you were using Newton-Raphson. So I kind of made that out that you were not using Newton-Raphson, but wasn't sure what were you using. So I think the first question gets answered over there. Maybe I'll open the floor for more questions from the audience.
Okay, I see. It's QQQs, right? It answers the question.
Yeah, actually. So I think the answer, QQQ got his answer probably. Maybe.
Yeah, I know his meaning. In linear problem, you can use linear iterative way, or you can also use Newton way. But I think there's no need to use Newton way, because it's very time consuming. Yeah, you can use. Maybe you can use inverse directly. It's more better. Yeah. However, in nonlinear problem, you must use nonlinear. The Newton way to get a solution. If it's a nonlinear problem. Yeah.
Rakesh, you have a question. You can ask your question.
Yeah. Wonderful talk. I have a question on that in FNO, it is regular mass, right? And in case of this PFEM, and that grid points are located in random kind of way. But how do you get those points? Like, what should be the location of those points?
I know your meaning. This point now we only use uniform random property. Uniform random property. Yeah. Okay.
Like
in FNO. Uniform. Yeah. In FNO we must get the grade, regular grade. Yeah. For example, let me show you here. For example, in this case, if you use FNO, you must use this way. The grade are regular. For example, this distance are same with this length. This length are same. However, in our Transolver, we use the random I mean the probability, I mean the probability density function is the uniform. Yeah, get this point. Yeah.
Okay, like these points are generated from some probability distribution.
Yeah, from the uniform distribution. I mean,
So
every position they have the same probability density.
I think what Rakesh is asking probably is, maybe I'll reframe it. He's trying to understand how did you generate the point net. So I think the input to the Transolver is a point net. So he's trying to understand how did you generate the collocation points that would be the input to the Transolver.
Oh, I know what you mean.
yes,
For example, I generate like this rectangular, and there is a uniform mesh, and then I get the point in the whole out. It's okay for you? For example, we can generate this in this rectangular domain because we know the whole shape. So we can get out of, I mean, every point. If the point in the whole, we can get out everything clear. So we can get this input.
Yeah.
So are those points? Those points are not specifically on some like in cos quadrature, or those are not points very specific to some location that should be adhered to it. It is random points.
You mean the collateral mesh?
Yes, in these distributions, like in the second Transolver, the points are randomly, right? So I was thinking about, is this generated with some any kind of different thinking, like for faster convergence of taking the points from some distance to the whole, or any kind of thing like that.
Yeah, maybe. Yeah. You mean I don't catch your meaning very clearly. So what's your meaning about this one? Hello?
Yes, yes,
Yeah.
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 Rakesh,
Could
maybe
you?
I'll pitch in. So
Yeah.
what Zizheng is trying to say is that he has the square domain, and within the square domain, he's using a uniform distribution to generate randomly spaced points. And then what he does is the points that lie within the cutout, he's removing them manually. So now he has points that define the geometry without the with the cutout. Does that help in
Okay.
understanding it?
Yes, yes, yes. Got it.
Okay.
Yeah. It's right. Yeah.
Any more questions, Rakesh?
No, thank you so much.
Okay. I think Wei has questions. Wei, go ahead.
Yeah. Wonderful talk. Yeah, I just want to continue that question. So how you manually cut that location, that random hole, or you use any tracks to cut that
Yeah.
random hole?
Random hole is from Gaussian random field. Yeah.
Yes.
Because yeah. For example, random Gaussian field, and you can make two bar, and if in this bar you will cut it. Yeah.
Okay, so maybe some values is higher than a critical value, and you just truncate that in your square. This
Yeah, that's
is
right. Yeah. Because
okay.
you can set the Gaussian random field. Because there are some hyperparameter you can use it. You can set two value, maybe two value. You can truncate. Yeah. So you
Oh,
can get this region.
okay.
Yeah.
But sometimes your Gaussian random field there will be at the maybe the edge of your squares, so you should manually select them and to
Yeah. I know
yeah
your meaning. I know your
yeah
meaning. For example, I don't want the hole near the boundary. Maybe in
yeah.
this way it's a 5 by 5. So I only random the Gaussian with a 4x4. So the whole
Oh.
only only you got it meaning.
Yeah,
Only
I got it.
Yeah.
Yeah, it's clever. It's so
Yeah,
clever.
thank you.
Okay. And I have another two questions. The first one is the structure you used in your paper is called, I think it's Transolver, right?
It's right, Transolver, yeah. I use the
Yeah.
Transolver.
So what is the main difference with your structure and the conventional Transolver? Maybe you did some modifications.
No, it's the same.
Oh, okay.
I use only the original Transolver as the backbone. I even
Okay.
don't make any change. I think it's enough, yeah. It's enough. It's a very good
Oh,
accuracy.
yeah.
Yeah.
And have you ever and my another question is, have you ever noticed that the same authors have published the Transolver plus plus? They call
I know
that
your meaning.
linear
Transolver
open.
plus. Yeah.
Yeah.
I know that, but I see. We because this initial work, I think we use the traditional framework. Traditional Transolver is enough. Yeah. We in the future we
Oh,
can use compare, because in the Transolver plus they want to make their problem in more larger problem. Yeah, I have
okay.
read the article. So if in the future maybe we want to solve the 3D or more complex problem, we can use the Transolver plus as the backbone. Yeah. But
Yes, yes,
I think
yeah.
it's the same. The framework is the same. We only change the backbone. Yeah. Maybe change. Maybe some years later, there is another famous guy propose another method is transceiver or transceiver. Yeah. We only change. Yeah. The framework only. Yeah.
Yeah, you can be the next famous guy. Yeah. Thank you. You answered my question.
Okay. Welcome. Yeah.
Maybe we have questions from Jump. You can unmute and ask your question. Jump, are you still online?
Is muted. Maybe go to the question that has been posted in the chat box. There is one nice question in the chat box.
Okay, yeah. So that person wants to ask you what about the
Okay.
composite
What
materials?
about?
Yeah, go ahead.
Okay. Okay, I know you mean. I mean, it actually, when we solve this problem, for example, this one, it is the composite material problem. It's because the modulus is different everywhere. So we have solved the problem. I mean, it is a composite problem, composite structure, composite material problem, because the material distribution are different everywhere. It's a Gaussian random field. It's okay?
Yeah, I think there is one more question in the chat.
Yes, there's one more. The final question, Yizheng.
Yeah, this one, please.
Yeah.
This one? Yeah, you mean make this way like agents, is right?
Yeah, so are you famous? Are you like familiar with Dr. Yangshu Choi's work on domain decomposition and foundation models with that?
Oh, I don't see his work. Yeah, it's my first time to see his work. Yeah.
Yeah, so so he's using his
I think
aspect.
it's a good future. Like the make like the Transolver like a backbone in the AI agents. Maybe I think. Yeah, I know. His work is very good. This guy, yes, very great scientist. Yeah. Maybe in the future, I will read this book. Yes, thank you for your recommendation. Foundation model in computational science.
And do you think that transolvers could be like used as a speed up accelerator for these traditional solvers? Like that's what your idea was for this presentation, right?
I don't know. Actually, I don't think they use Transolver based work. Yeah, because Transolver is a very new way. Yeah.
Okay. I think I would want to ask the audience if there are more questions.
This one, right? Do you have any idea how graph Fourier neural operator? Yeah. Maybe in the future, I think you can compare a lot of ways, like the graph Fourier neural operator or the other way. Because graph Fourier neural operator, it can solve the complex geometry problem. Yeah. But maybe in the future you can compare if you solve the Transolver. But I think because in this paper, as you can see in this paper, Pangu model, he solved a very complex problem. It's a numerical weather prediction. He proved that the transformer-based way is very good compared to FNO or deep or net. If we solve the problem, it's very complex. Yeah. Maybe it has a good potential to use a transformer-based way. Yeah.
Yeah. Okay. I think we are already out of time.
Maybe
Shobik, you want?
let us try with, I think, Jump maybe me online now, maybe because he is raising hand once more. Maybe
Okay. Yeah. Jump. Please go ahead. Yeah. Jump, are you online now?
Yeah, he's online. He or she, I don't know, but unmuted also. But maybe we are having some problem with the mic. Maybe. Yeah, we can't hear you. Sorry. Yeah, I mean, maybe you can always write to
Zizheng.
Yizheng,
Yeah.
right? You can always write to him, and I'm sure he will respond because you were not audible. So yeah, Samdutta, maybe you can wrap it up.
Okay. So thank you so much, everyone, for tuning in today. And thank you, Zizheng, for taking your time to present
Okay.
this work.
It's
And
my honor. Yeah. Hello.
it was
It's my
wonderful to
honor.
see you.
Thank you. I think
Okay.
I very enjoy it. It's very wonderful. Yeah.
Thank you so much. Thank you, everyone. And again, we'll see you next week. So next week, Zizheng, we have the author of Transolver presenting in this seminar.
Oh, you mean the author of Transolver? Wu Haixi?
Yeah.
Yeah. I know him. I'm familiar with him. He's my friend. Yeah. Yeah. Maybe I will I will join the meeting next week.
Absolutely.
Yeah.
Absolutely.
Yeah.
It'll be wonderful
And
if you can join. Yeah.
yeah. I will join. There is interesting like this work. For example, let me introduce you. This guy, yeah, Transolver order, and this one, Hao Zhongkai, he is our work the second order, yeah, because he give me a lot of idea about that. So, Hao Zhongkai, he is also very famous in the Transolver based operator learning. Yeah, maybe I will ask him to join
Absolutely.
the talk.
Yeah. Yeah. Thank you so much, and thank you, everyone.
Okay. Thank you. Bye.
Bye. To someone who actually just mentioned on the chat, we have the same Teams link for the next week, and we'll
Yeah,
also post.
it's the same link every week.
Yeah. Great. Thank you so much, and everyone have a nice day. See you.
Thank you.
See you. Bye.